So section 4.2 in college algebra is all about exponential models. Now we talked about the actual functions in the previous lesson, and that was fine and dandy, but the models are where we really get to use the exponential functions. So we're going to look at a few specific examples of different exponential functions. If I can get my cursor to work. There we go. The first model that we use a lot, especially in biology, is doubling time. So the population of bacteria or whatever you're talking about is equal to the initial population times 2, and then his exponent is t divided by d power. T represents the time allowed for the population to grow, and d represents the amount of time it would require that particular sample to double. So depending on what type of bacteria it is or whatever we're talking about, that d is going to be probably be given to you, but it's going to be different for different samples. So this particular example, number 3, is about population growth in our textbook, and it's about a fruit fly. And population, fruit flies don't live very long. And they studied some fruit flies, yada yada, keep reading. It says the doubling time for a population of fruit flies is 2.4 days. What they just told us was the d for this formula. And the label is in days. I have a feeling everything for fruit flies is labeled in days, and if it's not, we need to make sure we convert it. So if we start with 5 male and 5 female flies in the population, how many flies should we expect to have in 1 week and then in 2 weeks? So right away I notice an issue with labels. They gave me the doubling time in days, and now they're giving me the question in terms of weeks. So first thing I notice is when they say 1 week, that's really a 7. 2 weeks is really a 14 for days, and then the part of the formula we're referring to is the t. So for part A, the t is going to be 7, and for part B, the t is going to be 14. And then the initial population, if it's 5 males and 5 females, that would be a population of 10. So the piece of knot, the initial population, is 10 flies. So for part A, using my formula, 10 flies, and then doubling up in the exponent, it's t, which is 7, divided by his doubling time of 2.4. And I'm going to type that in my calculator in the home screen, so I just need to compute it. And let's see here. 10 times 2, 2 is the base of this power, of this problem. 7 divided by 2.4 power. Whoops, that is not a 4, Bruzo. So the population after 1 week is going to be roughly 76 flies. And then for part B, very similar question, except the t is going to change to a 14. So same setup, except now it's a 14 divided by 2.4 power. So I'm just going to pull up my previous entry by doing second and then enter. And I'm going to go and edit it, by typing a 1, and then I'm going to have to insert the 4 because the digits wouldn't match up. Otherwise it's going to overtype. Yay! The population for the fruit flies has now doubled to 570. Okay. Now, they didn't tell us anything about how long a fruit fly lives, so this might be a nice follow-up question if we were actually studying this. If a fruit fly does not live more than 2 weeks, typically this population number is not quite right, so I guess we're assuming that they do live, but I'm pretty sure I don't think fruit flies live that long. Alright, next question. Number 2 is a similar question, except I just made this one up. Harlem City has a doubling time of 7 years, so that was the D for the formula. 2008, this is the initial population, so that's our initial population. And 2010, if I think about 2008 to 2010, that is a difference of 2 years. So for my problem, times 2, and then up in the exponent, t divided by doubling time. So when I type that in my calculator, 132,000. Now if this was a really large number, like in the millions, you could do it in terms of a million. Cut off the zeros basically. Just make sure your answer, oops, look what I did. I was yapping and I forgot my parenthesis. There we go. So the population, it's not enough time for it to double, but it sure did grow. So our population is about 160,910 people. Oops, it's a 1. And it's people, so you always want to round to the nearest whole person. Okay, next example is a half-life. So exact opposite of doubling time. Instead of growing or doubling, we're decaying or going down by a factor of a half. So very similar, except now the base is a 1/2. So example 5 in our book is about insecticide, DDT, that's no longer allowed to be used because of its effects on human growth and animal growth and plant growth. So a farmer uses 25 pounds of DDT and the half-life is 12 years. How much is still active after 5 years and 20 years? So the initial amount of DDT that they used was 25 pounds. And luckily it will decay. So that's a variable h, by the way, right there. The half-life of DDT is 12 years. So for the first part of the question, it says 5 years later, how much is left? So the t will be equal to 5. And then for the second part of the question, 20 years later. So, of course, it'll be less and less every year, but the idea is we want it to be nothing. Unfortunately, it'll never be nothing, but it'll be close. So in my calculator, I'm going to type initial 25 times. Now, if you did 0.5, you don't need parentheses, but if you do 1/2, you're going to need parentheses. Oh, goodness. 1/2. And then to the t over half-life power, so 5 over 12. So it will not have halved by this time, but it will be less. It's 18.7 pounds, roughly. And then for 20 years, I'm just going to cheat, and I'm going to pull up my little previous entry, and I'm going to overtype it. I'm going to insert the 0 so I don't overtype the division. And this time it will more than have halved, however you say that. It's about 7.9 pounds. So still 20 years later, still a lot of DDT active in that soil or wherever they were measuring from. Okay. Next question. Oops, I lost a question at the bottom there. The half-life of an isotope is 415 years, so that is the H. That's an H, goodness. 15 grams originally, so that is the original amount. How much is left 200 years later? That is our T. So 15 grams times 1/2, and then up in his exponent, time is 200, his half-life is 415. So I know from the time that they gave me, it's not going to have halved by this point, but it will be less. Let's figure out how much less. This is, I don't know if there's any examples coming up here, because I haven't looked at this lately, but they talk about carbon dating when they look at fossils, and they are allowed to do that because of the isotope of carbon that's in the fossils. They can date it through its half-life and how much is left in the sample. So it's kind of neat. There's a lot of math in archaeology. So, roughly 10.7, and a label on this would be grams. Okay, if they wanted a more accurate reading, they'd be very careful about how they rounded. Okay, continuous growth. We saw this formula in the last section. PERT is continuous growth. So when I look at number 7 on that same page, it says the world population is 6 billion people right now. So that must be my initial population. And I'm not going to write all the zeros. I'm just going to write 6 billion. So I'm going to do it in terms of a billion. And it grows continuously at a rate of 1.7%. So I'm going to change that to 0.017. What will be the population in 10 years? So this is a pretty easy question. We're just going to type it into our home screen of our calculator. And then remember, I'm going to do it in terms of a billion. So 6 times e to the 0.017 times 10 power, r times t power. Make sure you have parentheses if you have the older math print, a classic print. If you have math print, you don't have to worry about parentheses. Just get out of the exponent when you're done. So roughly 7.11 billion people. Oh, it said 2 significant digits. I'm sorry. So we should eliminate that extra 1. 7.1 billion people. And again, it's an estimate. Alright, same type of example here in an account that's compounded continuously. So again, we're going to use PERT, 5% per year. There is this much in an account after 10 years. They want us to figure out the original amount. So the A, the final amount, is the 4125. The P is something I am not aware of. So E is a number, and then the R is 0.05 times 10 power. So the first thing I'm going to do is I'm going to calculate this decimal right here, and it's not going to be pretty. So E to the 0.05 times 10 power, and that's lovely, 1.649 we can round that to. So we have 4125 equals P times 1.649. And now to solve for P, I'm just going to divide by 1.649. Now the more you round off that value, the more you're going to differ from the actual value. So if you're worried about it, just keep more decimal places. But 4125 divided by that answer. And notice when I type it this way on my calculator, by bringing up the answer, I'm not going to be rounding it off at all. And this is money, so it looks like our initial investment rounded to the nearest hundredth, because it's money, is roughly $25.0194. You might be off by a cent if you rounded off that number like I showed in the work, but I did not do on the calculator. What else they have for us today? Oh, that's it. So 4.2 shouldn't be that bad. Good luck.